بسم الله الرحمن الرحیم. روز شنبه هست 24 اردیبهشت ماه 1401 جلسه دهم درس زمین آمار در خدمت عزیزان هستیم. If you remember, in our Monday session we try to fully dig into various aspects of either linear or non-linear curve fitting, and then if you realize we try to offer a few unanswered questions on variogram modeling. Today, the general problem statement is this. We are given a single partial realization of a random function. Then we are asked to estimate the theoretical variogram. It might help to answer this question. First, why do we need variogram? Any comment? Any feedback? Why do we need variogram for estimation? Can we go for estimation without knowing the model of spatial variability?
برای که بدونیم که تخمینی که ما میزنیم به چه حد قابل اطمینان و قاعدتا نیاز داریم برای variability رو داخل اون محدوده از حالا داده هامون بدونیم.
I shared 2 files with you on Friday. The title of those 2 files were Roadmap 1 and Roadmap 2. And in those 2 files I try to provide a roadmap, perhaps to say, for this question with regard to why do we need to go for variable. In any estimator, be deterministic or stochastic. You were told about deterministic approach in your either Bachelor of Science or Master of Science, and today we would like to go for stochastic estimation. Either in stochastic or deterministic estimation, the estimated value of y at a point which is not sampled can be written as a linear combination of observation. Then remember, this is our problem statement for today, and we do have another problem statement for the entire course. And that problem statement is given a single partial realization of a random function then we are asked to estimate the attribute under consideration at the point which is not sampled. Let me repeat the question again. Why do we need variogram for estimation? Why do we need to know variogram, of course, theoretical variogram, to solve this problem? And that's a very good, perhaps challenging question. Why do we need theoretical variogram to go for solving this new problem? And this is the general problem statement from the beginning of this course up to the end. Estimated value of y at a point which is not sampled can be written as a linear combination of observation. We do know this because it is here. We are looking for this. So, if we know this and we are looking for this, what we need to know is to know these lambda. Lambda 1, lambda 2, lambda 3, up to lambda 3. And then, how could it be possible to compute these coefficients? Please pay attention. Please pay attention. It really doesn't matter whether you are in continuum mechanics or you are in stochastic mechanics, geostatistics. The estimated value of y at the point which is not sampled can be written as a linear combination of observation. And then if you want to find these coefficients, you have to define a framework for yourself. And the framework for you is going to define your residual. This is the estimated value, and you have to subtract this estimated value from either observed value or true value. And then that's going to give you the residual. And then you have to impose two conditions on your residual error, so to say. The very first condition is going to be unbiasedness condition. We are going to talk about it. Expected value of residual has to be 0. And then the second condition you have to impose on your residual is to minimize the residual. Today, after solving this problem, I will compare and contrast this with our previous lecture to see how it will fit into least square that you are familiar with. But as soon as you try to minimize the variance of residual, sooner or later you will be faced with either covariance function or variogram function. And that is why we need variogram. The second question that I would like to raise and answer from the very beginning of this session, why do I interested in theoretical variogram and not theoretical covariance function? Remember that in geostatistics, geostatisticians prefer variogram compared to covariance function. And in our midterm exam, I try to raise this question in our midterm exam, asking, offer 3 reasons why geostatisticians prefer variogram function compared to covariance function. It is quite important for you to realize that if you know theoretical variogram or experimental variogram, sooner or later you can compute covariance function using R sub h plus gamma of h equal to R0, which is the relationship between covariance function and variogram function, provided that your random function is stationary. That if your random function is not stationary, then you cannot use that. You have to exclusively focus on your variogram because covariance function is not available. Therefore, I raised 2 questions and I tried to answer those 2 questions at the very beginning of this session. Why do we need to compute theoretical variogram? Sooner or later, you will realize that if we want to compute this coefficient here, we do need to know the variogram model. The second question, why do we raise this question in this way? Another way of writing this question is to say, given a single partial realization of a random function, then find theoretical covariance function. But I did not write covariance function because covariance function is independent. But variogram function is not independent. Variogram function is more general term. You can solve numerous problems with variogram function, but you cannot solve those problems using covariance function because covariance function is not available, say, for Brownian motion. Now, let me focus on this question and then move to this question that I share to electronic file with you. In fact, this question can be collapsed into a new question based on what we said for the last 2 or 3 sessions. Because if you are given a single partial realization of a random function, then at first you have to compute experimental value. Therefore, let me put it this way. Given gamma hi versus hi for ri from, say, 1 to p. Find this is my experimental variogram, which is a table, not a closed form function. And this is my theoretical variogram. When you are faced with this question, the very first thing that you need to do is to use this single partial realization of a random function to compute this row here. And then as soon as you have the experimental either omnidirectional or directional variogram, what you need to do is to convert experimental variogram into theoretical one. We have 2 schools of thought on variogram modeling due to مکتب فکری. In fact, scholars, investigators, graduated from the Department of Geological Science, such as Stanford University, follow one school of thought. Scholars, investigators, graduated from Civil Engineering Department, follow another school of thought on variogram modeling. A person such as Kitlandis are coming from Civil Engineering Department, Stanford University. A person such as Jornal and his co-workers are coming from Geological Science Department, again from Stanford University. According to a school of thought emerging from Geological Science Department, if you want to compute experimental variogram, if you want to compute theoretical variogram, you have to, on a experimental variogram alone. And you may ask, what do you mean by honoring experimental variogram? Let me tell you the second school of thought, and then you try to compare and contrast these two schools of thought to see how they differ from one another. According to the second school of thought emerging from Department of Civil Engineering, hit on this. It's quite interesting for you to know that both departments are coming from the same university, Stanford University. Geological Science Department, where you are coming from, and Civil Engineering Department, where you are coming from. According to the second school of thought, if you want to compute a theoretical variogram, you have to compute the original data. Can you have in your own word how these two schools of thought differ from one another? First school of thought, honor experimental variogram. Second school of thought, honor original data. How come? Remember, I introduced a textbook written by Ward in 1974, and the title of that book is Nonlinear Parameter Estimation. And in that book, if you open the book, read the first 2 or 3 pages of chapter 1, sooner or later you will realize that in solving a problem like this, you have 2 degrees of freedoms. The first degree of freedom is what would you take to as your mathematical model, because you need a mathematical model for gamma as a function of h. That is the first degree of freedom. The second degree of freedom is the measure of goodness. According to the first school of thought, Geological Science Department, your good fitness criteria, your measure of goodness is to minimize the error between experimental variogram and theoretical variogram. That is the first school of thought. If this is your experimental variogram and that is your theoretical variogram, you have to compute this theoretical variogram in order to minimize the error emerging from this and this. Just like what I did in my previous lecture. In fact, this will act as y, and this h will act as x. It really doesn't matter whether I write my original question in this way or write my original question in this way. Given xi, yi for all I from 1 to p, I try to use p here in order to differentiate it between n and p. This n is the number of data, this p is the number of intervals for your separation, maximum separation distance, or 2/3 of maximum separation distance. And then here you would like to find a functional relationship between y and x. That's how we did in our previous lecture. We tried to solve this problem. This y here will act as gamma h, and this x here will act as h. This is how these two problem statements can be connected to one another. Here you have 2 degrees of freedom to solve this problem. The The first degree of freedom is to decide on a functional relationship connecting X and Y. Remember that I introduced a program so-called table curve. You can delineate it in your Googling, and in that program you have 3,000 mathematical models incorporated into that program, table curve. The second degree of freedom here is to define your goodness criteria, fitness criteria, measure of goodness. Remember that we have a variety of choice to find the parameters of this functional relationship. Here, when we want to solve this problem, we have a totally different qualitative measure at first, and then we have to convert it to quantitative later on. The qualitative goodness or measure of goodness is this. According to the first school of thought, we have to compute theoretical variogram honoring the experimental variogram. Which means here, we have to obtain this y trying to honor observed y. Forget about original problem. According to the second school of thought, we have to compute theoretical variogram honoring the original data. What do I mean by honoring the original data? Here, by honoring, according to the first school of thought, I have to mention that we have to minimize the sum of the square of observed and theoretical. But when it comes to second school of thought, we have to assume a theoretical variogram, go for estimation, obtain y at every point which are sampled, and then subtract observed value minus estimated value, square them, add them together, minimize that square to obtain the best theoretical value. Can we, Mr. Robin, could it be possible to give us a reference in order to further dig into these two schools of thought? Yes, Kitandis. Kitandis favor the second school of thought on variogram modeling, but at the preface or chapter 1, he tried to compare and contrast his own textbook with other textbooks in conventional literature, touching on a few points where his textbook differed from other conventional geostatistical textbooks. Therefore, if you want to dig further into these two schools of thought, you have to read the preface of Kitandis' textbook or chapter 1. In that textbook, he tried to compare and contrast two schools of thought. What do we mean by honoring experimental variogram? What do we mean by honoring original data? I shared a document with you, and in that document I introduced it in my previous lecture. This document called variogram.pdf, and in this document I introduced a number of theoretical admissible variogram. And I'm going to share a paper with you later on today, and the title of that paper, it was written in Water Resources Research, and the title of this paper is on the problem of permissible covariance and variogram models. It was written in 1984 by George Christophs. And in this paper, it talks about the theoretical background regarding the idea that we cannot disvariogram theoretical background from any function. We have to limit our function to positive definite function. And positive definite function has something to do with linear algebra that you might have a chance to expose to linear algebra, positive definite function, positive definite matrix, and so on in that course. Now, how should I proceed to solve this problem? It's very important. And as some of you, or all of you, might want to work in academic media in your professional life, it's quite important. If you want to solve a problem, you have to build this problem on previous student knowledge. به فارسی خیلی مهم هست، چون خیلی از شماها تو محیط آکادمیک مشغول به فعالیت میشید، یا آموزشی یا پژوهشی، امیدوارم تو باشه، نه اینکه از دیپارتمان جیولوژیکال ساینس فارغ التحصیل بشید، از دیپارتمان سیویل انجینیرینگ فارغ التحصیل بشید، بعد برید توی بیزینس
بیت کوین تهران
بیت کوین و اونجور چیزا.
الان تمام دانشجو کارش می‌کنه.
امیدوارم میتونم بشه. البته مقصر شما نیست. باید دانش جدید رو سوارش کنید روی دانش قدیم دانشجو که چه احساسی بهش دست بده. آقای مهندس صاحبی، موقعی که دانش جدید رو بیلدش بکنید، سوارش بکنید دانش قدیم دانشجو، احساس قرابت نمید. ای که من میدونستم، یکی جدید نیست، این من میدونستم. In our Monday session, we try to dig in full detail into this question. And today, at first, we say this xi is basically hi, and this yi is basically gamma I. We are given hi and gamma I for I from 1 to p, and then we are asked to estimate a functional relationship connecting gamma to h. And it's quite important to acknowledge the fact that you cannot use table curve to solve this problem or this problem. Why? Because out of that 3,000 mathematical model, some of them are not positive definite. When it comes to variogram modeling, your theoretical variogram, your function has to be positive definite. Or the matrix extracted from that theoretical variogram has to be positive definite. You people, particularly Mr. Mir Ahmadi, I have no idea if Mrs. Rajabzadeh has also taken a course on linear algebra. Have you ever? If you are familiar with linear algebra, you are more or less familiar with positive definite matrix, not positive definite function. If you are given a matrix and you would like to check whether this matrix is positive definite or not, a given matrix is positive definite if every eigenvalue extracted from this matrix has to be positive. That's it. You have 4 options to check whether a matrix is positive or positive definite or not. One of them is this: positive definite, positive semi-definite, negative semi-definite, and so on. These are terms emerging from linear algebra. Now, how could it be possible to solve this problem, building this problem in your previous knowledge? In your previous knowledge is this. And at first you have to limit your functional relationship between gamma and H to be positive definite. As soon as you realize this fact, you will eliminate functions which are not positive definite. This document here gives you a number of positive definite variogram model. The very first page of this is Gaussian variogram model, and the Gaussian variogram model is given by sigma 2 1 minus exponent of minus h to the power of 2 divided by L2. This is Gaussian variogram model. Sigma 2, 1 minus exponent minus h to the power of 2 divided by L2. The second page concerned with exponential variogram model. The third page with spherical and so on. And then we have power model. This is the power model. And we have linear model. When we want to solve this problem, if you want to restate your problem in terms of this theoretical variogram, it makes a lot of sense to say, if I'm given experimental variogram, and I was told that my theoretical variogram is Gaussian, then what I need to do is to obtain this sigma 2 and this L2. If my theoretical variogram is power model, then my task, my job is to obtain this A and B. If my theoretical variogram is a linear variogram, then my task is to obtain this A and B. In fact, if your theoretical variogram is linear, then you have already solved this problem. Because in our Monday session we talked about this problem in more detail. This problem here is very similar to what we have here. You have to replace this h with x and this gamma with y. And then if your school of thought is the one emerging from geological science department, you have to minimize the sum of the square between observed value and simulated value. If your school of thought is emerging from civil engineering department, quite interesting, and you were told that your theoretical variogram is linear, what you need to do is to obtain A and B first, but do not try to concern about, of course you have to minimize the sum of the square here as well, according to the second school of thought. But you should not stop at that point. You should go ahead, use this theoretical variogram, estimate every y at those points, and then toward the end of this story, at every point in space you have two numbers. One where you observe and one where you estimate. Subtract them from each other, raise them to the power of 2, and your variogram is going to be the best if the sum of the square between observed value and estimated value is minimum. Can you see how you should proceed to follow the first school of thought and then the second school of thought? It seems that if you want to focus on second school of thought at first you have to implement the first school of thought to obtain the parameters, and then do not stop at that point. Continue, estimate the attribute under consideration at every point where you have observation, and then try to subtract them from each other, raise them to the power of 2 in order to eliminate the minus sign, and then see which variogram will give you the best or minimum sum of a square between estimated value and observed. Here, if you collect these various theoretical variograms into this relationship, is it okay to represent these variogram in this way? This x is basically h, and this y is basically gamma. And your job is this, given xi, yi for all I from 1 to p, then find y here you have 2 unknown here. The very first unknown is f. The second unknown is the parameters a and b. By f, I mean, should I choose Gaussian variogram, theoretic Gaussian exponential variogram, power variogram, and linear variogram? This operator here concerned with the type of variogram to choose. This f here, if you want to make a correspondence between this f and a program so-called table curve, this f here implies that you have 3000 f in your table curve, and you have to choose one out of 3000 f in table curve. And then when it comes to this a and b, here you have to fix your f, and then based on that f try to find the parameters. Now, I have to have another definition here, and this definition has to do something with nature of variogram. If you increase this separation distance here, if you put this h equal to infinity, what will happen? If you replace this h here with infinity, the exponent of this will become 0 because of this minus sign, okay? And then it means that if you increase the separation distance, at some point gamma will approach sigma 2 because this part is 0. What about these two? If you replace this h here or this h here with infinity, then gamma will become infinity as well. We have to differentiate between these two types of variogram model. We call this type of variogram transitive variogram, and this variogram where it has infinite capacity for dispersion. If you increase h, then gamma will increase without limit. We call this variogram to be non-transitive. Transitive. If you increase h, then at some stage, at some point, gamma approaches the global variance, sigma 2. Exponential function, Gaussian function, spherical function behave like transitive variable, where if you increase h, then at some point, gamma will approach global variance. But when it comes to power model and linear model, if you increase h, then gamma will increase without limit. We call this type of variogram non-transitive. It has infinite capacity for dispersion. If this f over there is linear, we are okay, because we have a chance to cover that in our Monday session. Today I would like to raise this question. What if the functional relationship between y and x is not linear? And by linear or non-linear, you can either interpret this linearity according to a statistical one or system approach. Here, the graphical representation of this or the graphical representation of this is not linear. Can you follow? If you draw this on y-axis, this h on x-axis, is the graphical representation of gamma versus h is not linear. Here, if you map gamma on y, h on x, again, when it comes to power model, it is not linear. But this one is linear. Why? Because if you map gamma on y, h on x, then it will become linear. Therefore, according to first school of thought linearity, where it is a statistical one, this one is not linear, this one is not linear, but this one is linear. Now, you have a number of mathematical models like this, which can be linearized. All you need to do is to take natural log or log of both sides. If you take natural log or log of both sides, you are going to get log of gamma h equal to log of a plus b log of h. By just taking log of both sides. And then if you call this y, and then call this a plus b x, then it will become linear. If you take log of both sides, you will fix this one. And then if you rename your variable, because if you have the experimental variogram for this, then you could take log of that number to obtain y. If you have experimental observed value for h, then you can take log of that number to reach this x here. And then it will become linear, which means you have a number of mathematical models where they can be linearized, like this. And the notion of making a functional relationship is linear is sometimes not that easy. Look at this relationship. Again, it is not linear. If you draw t, or perhaps better put this x to make it more familiar. If you map x on x-axis and then y on y-axis, draw it will look it is not linear. But you can make it linear in order to get benefit from linear least square. How? All you need to do is to write it this way. And then this y, which is this reciprocal of original y, is equal to ax plus b. Again, it will become linear. The beauty of physical session is that we have face-to-face discussion and we can dialogue between one another to eliminate the ambiguity in our discussion. Please raise your hand, ask question if you are not following me on the board. When it comes to this relationship cannot be linearized. Why? Why we can't linearize this relationship? Here we take natural log or log of both sides to make it linear. Here we try to use another trick, making the reciprocal of dependent variable to make it linear. But when it comes to this relationship, it cannot be made linear. The implication of not being able to linearize it is to focus on nonlinear regression. Therefore, if you are asked to solve this problem, and for more than 90% of the time, this f cannot be linearized. You have to solve this problem using nonlinear regression. If you want to compare linear regression with nonlinear regression, again, one possibility to acknowledge the fact that if you want to find the parameters of this A and B here, which is again like this relationship here. For the moment, assume that I cannot linearize this relationship. Just assume I cannot linearize this relationship. How would it be possible to proceed based on our Monday session to obtain A and B? I have to put I here. I have to put I here. And then, because of these are the observed value of y and x, then I have to add epsilon. That is how epsilon will come into our consideration. And then you have to cast your objective function. Your objective function f, now I have to use g, is going to be sum of the square error. That is what I remember from Monday session. And then if you want to replace this epsilon I here, what you need to do is to subtract this from this epsilon and then replace it out there. I just replace epsilon with what I have. Now, you do not have any choice on x and on xi and yi to make this g minimized, but all you need to do is to play with a and b. What would be the numerical value of a and b to make this g minimized? What you need to do is to take partial derivative of g with respect to a, put it equal to 0, partial derivative of g with respect to b, put it equal to 0, and then you have two equations with two unknowns. Partial derivative of this g with respect to a. These two will become here. And then you have to obtain the partial derivative of what you have inside with respect to a will become minus xi to the power of b. That is the partial derivative of the content of this bracket with respect to a, and then you have to multiply this by y sub I minus a xi to the power of b, 1 power less, and then put this equal to 0. When it comes to partial derivative of g with respect to b, please pay attention. Your partial derivative with respect to b. Again, you have to have I from 1 to p, and then you have to bring that to in front of the bracket. How about partial derivative of xi to the power of b? Can you comment on how could it be possible to obtain partial derivative of xi to the power of b when it comes to partial derivative with respect to b, not x? See, if you have a function like this, this is the same as xi to the power of b, because xi is a number. But this x here is variable, this b here. How could it be possible to obtain the partial derivative of y with respect to x here? You have to take natural log of both sides, which will become x, and then take derivative of both sides. The derivative of this will become y prime over y, and then the derivative of this will become x, natural log of a. And then you were looking for y prime, therefore y prime is equal to a to the power of x times natural log of a. You can use this relationship to find the partial derivative of this content with respect to b. It will become minus xi to the power of b, and then natural log of xi. That is how to obtain the partial derivative of this with respect to b. Xi act like a, and b act as x. And then you have to multiply this by 1 power less. What happened? This minus 2 cannot be 0. Forget about it. Xi to the power of b times yi minus a xi to the power of b. That is your first equation. And your second equation, again, minus 2 times b cannot be 0, and you are left with I from 1 to p, xi to the power of b, natural log of xi times y sub I minus a xi. And your job, because you are given x and y, your job is to solve these two system of nonlinear algebraic equation and obtain a and b. Can you comment on the nature of these two nonlinear algebraic equation? Can you tell me, if you multiply this y by this xi, how many terms you are going to have? You have to replace this I from 1 to b. Therefore, the first term, xi to the power of b times yi, has to be expanded I from 1 to p. And then you have to multiply this by this and then expand it from y equal to 1 to p. All together, you have 2 times p terms. Because p term for the first one, p term for the second, and they are highly nonlinear. When it comes to this one, again you have to multiply this by this, expand it from y equal to 1 to p, multiply this by this, expand it from y equal to 1 to p, altogether you have 2p nonlinear terms. I will consider these two systems of nonlinear algebraic equation to be highly nonlinear. I will put a dead end. What do I mean by dead end? It is not possible to solve. Simply, it is not possible to solve this system of nonlinear, highly nonlinear algebraic equation. And that is why we prefer to linearize it first and then use what I said in our previous lecture, both from matrix point of view and from direct approach point of view to find the system of equation in terms of reality. What should we do here? It's very important to know why you first cannot linearize this f here, and if you want to focus on nonlinear relationship, solve it through this approach, sooner or later it will become dead end. because you have to expand the terms and it's quite nonlinear, highly nonlinear for solution. Question, any comments, any concern, any ambiguity that you want to ask? How could it be possible to compute A and B assuming that F is nonlinear, like what we have here? And even it is important to realize that it cannot be linear. Here we should look for, please pay attention, here we should look for an iterative relationship for A and B, so that for first iteration we obtain an initial value for A and B, and then put this initial value into the mechanism that we introduced to find A1 and B1, and then use A1 and B1 to obtain A2 and B2. Sooner or later, define a stopping criteria to satisfy that criteria. Therefore, the mechanism in order to solve this problem is to obtain a relationship where you incorporate A0 and B0 into that relationship to obtain A1 and B1. Go ahead. We should find that relationship for trial and error, because that relationship is going to be a closed form function. And then use A1 and B1 to obtain A2 and B2. And then move on, keep going to find AK and BK. And then if you plug AK and BK into that relationship, sooner or later you will realize that AK plus 1 and BK plus 1 will satisfy your stopping criteria. I know we'll talk about stopping criteria soon. مسئولیت ما، رسالت ما برای حل این مسئله‌ای که اینجا به ددهند خوردیم نتونستیم این رو ادامه بدیم، این خواهد بود که این مسئله رو میخوایم حل بکنیم، دنبال یه سازوکاری بگردیم، دنبال یک پروسیجری باشیم که اون پروسیجر به ما بگه اگر A0 و B0 رو گذاشتی تو اون رابطه بتواند A1 و B1 رو بده، بعد A1 و B1 رو گذاشتی بتونه A2 و B2 رو بده و همطوری رو ادامه بدی. اگر A1 و B1 رو گذاشتی اینو بده و این استاپینگ کرایتریا رو ارضا. خب first of all let me define my objective function. If y is equal to f x a and b, this is a functional relationship which cannot be linearized. My first task is to be able to obtain that iterative relationships. Therefore, if I put I here, then I have to add what? epsilon I here. Okay? Just like what I did out there. And then my objective function is again this. I have to replace epsilon I with yi minus this. This is my objective function. And I have to obtain A and B so that G will become meaning. Of course, I have to know F. I have to create my functional relationship, which means that I have to identify this. Now, if I was told that AK plus 1, BK plus 1 will satisfy my stopping criteria, what does that mean? I was told that A and this K plus 1, B, K plus 1 will satisfy my criteria. That means G as a function of AK plus 1 and BK plus 1 will satisfy my criteria. We have three measures. Please pay attention. We have three measures when it comes to stopping criteria, and these are from a numerical analysis, by the way. A 2-credit course in your Bachelor of Science degree. We were told that if you plug these numerical values of AK plus 1, B plus 1 into this relationship, it will satisfy your stopping criteria. We have three stopping criteria in making this iterative process to conversion. Let me comment on three stopping criteria and then see which one is going to be the one we are going to incorporate here. If you call S to be a vector of A and B, then by SK I mean AK, BK, and by SK plus 1 I mean AK plus 1, BK plus 1. In a sense, this is going to be my S0 Yes? And that's going to be my S1, S2, keep going, SK, and S. I was told that when I reach this stage, my stopping criteria has been satisfied. What do I mean by stopping criteria? Based on what I introduced here, the first stopping criteria is to say I would like to have the norm of Sk plus 1 minus Sk to be less than or equal to a given low number, say n to the power of minus 3. That is the first stopping criteria. And you may ask me, how could it be possible to compute this? What you need to do is to say, if you want to compute the norm of this, you have to specify your measure of length. If your measure of length is Euclidean, then it's going to be ak plus 1 minus ak to the power of 2 plus bk plus 1 minus bk to the power of 2, and then you have to raise this to the power of 1 over 2. That is Euclidean stopping criteria. Then again, if you want to consider this stopping criteria to see at what stage you have to stop. Plug this here, and then at every stage compute this norm and see if it will satisfy this. And that's how to compute this norm of this vector. The second stopping criteria to consider is to focus on absolute value of ak plus 1 minus ak to be less than or equal to 10 to the power of minus 3, and absolute value of bk plus 1 minus bk to be less than or equal to 10 to the power of minus 3. That is the second stopping criteria. Please pay attention. It may happen that when you move from this line to this line, the first stopping criteria, which is A2 minus A1 will be honored, but when it comes to B2 minus B1, it is not. You have to keep going so that both of them are satisfied simultaneously. That is the second stopping criteria. The third stopping criteria is to argue that the objective function itself at a particular point satisfy a relationship like this. No, one of them. You will move from this to this, compute g sub a1 b1 from where? From this relationship. Because you do know x1, xi and yi from I equal 1 to b. You do know a1 and b1. You can easily compute what? G sub a1 b1. And then compare it with this number. If it is okay, stop. If not, move to this next step. If not, go to the next step. And then see, of course, one of them has to be in place, not all of them at the same time. Either stopping criteria number 1, stopping criteria number 2, stopping criteria number 3. And if you remember to my Monday session, you have some other stopping criteria as well. Can you tell me one of them regarding minimum, maximum problem, minimax problem? You could have a stopping criteria like this. Minimize maximum of AK plus 1 minus AK, absolute value of BK plus 1 minus BK. That's another stopping criteria. At every stage, you have to compute the absolute value of this and absolute value of this and try to minimize it. Say, I would like to have this less than or equal to, say, 10 to the power of minus 5, as an example. What I understand from literature, out of these 4 stopping criteria, the most used stopping criteria is 3. Is to try minimizing or finding a threshold like 10 to the power of minus 3 and see if this numerical value of the sum of the square will satisfy this criteria. Now, referring back to our original problem, it makes no sense to start taking partial derivative of g with respect to this, because you will sooner or later run into this dead end. Therefore, you have to obtain an iterative relationship to be able to move from this line to this line, from this line to this line, from this line to this line, and then stop your iterative procedure based on one of these stopping criteria. What I am going to do, please pay attention. This is Rajab Zadeh, this is Zare. What I'm going to do is to use this relationship and expand this term using Taylor series expansion around X, AK, and BK, and see what will happen. YI. What I'm going to do is to expand this around XI, AK, and BK according to Taylor series expansion. It will become minus f sub xi, AK, EK, because I would like to expand it around this point. And then minus AK plus 1 minus AK times partial derivative of f with respect to A computed at, of course, x is equal to xi, A equal to AK, and B equal to BK. This is the second term of the Taylor series expansion. Minus BK plus 1 minus BK partial derivative of f with respect to B again. You have to compute this at x equal to xi, A equal to AK, and B equal to BK. Can you comment on what happened by expanding this around xy, AK, BK? Your objective function AK plus 1 BK will become linear with respect to AK plus 1 BK plus 1. This part here, of course, you have to put 2 here. This 2 is again the same as this 2 here. This terms inside this bracket is linear with respect to AK plus 1, BK plus 1. Therefore, if you take partial derivative of G with respect to AK plus 1, put it equal to 0, take partial derivative of G with respect to BK plus 1, put it equal to 0, you will find the iterative relationship that you are looking for. What would be the, by the way, you have to put these two now. You have to find the partial derivative of what you have here with respect to AK plus 1. Can you tell me what is going to be that partial derivative? This has nothing to do with AK plus 1. It is 0. Because there is no AK plus 1. This has nothing to do with AK plus 1 because there is no AK plus 1 in this. The only term that you have A plus 1 is this one. And then the partial derivative of this with respect to A plus 1 will become minus this. And then you have to multiply this by the same term, 1 power less. Please pay attention that you have to compute partial f with respect to A at this. You have to compute partial f with respect to A at this point, and so on. When it comes to this relationship, again, I has to go from 1 to p, this to here, and then you have minus partial f with respect to b, and then 1 powerless. You can simplify this relationship, knowing the term that you know on one side, the term that you have no idea on the other side. If you multiply this by this term here, it is known, because this has to be computed at a known number, this has to be computed at a known number, because a, k and bk are given, and you are looking for ak plus 1, bk plus 1. Therefore, minus 2 will cancel out because this minus 2 cannot be 0. And then this time this will go on the other side. And then this times this times this will remain on one side. Therefore, let me write it here. AK plus 1 minus AK times summation I from 1 to p partial f with respect to a to the power of 2. Why to the power of 2? Because you have to multiply this by this. And this times this will become 1 to the power of 2. And then why did I bring this outside? Because this has nothing to do with index of summation. You can bring it outside. Okay? Plus bk plus 1 minus bk times I from 1 to p partial f partial a partial f partial b equal to, and then this times this will go on the other side. It will become summation I from 1 to p partial f partial a y sub I minus x of xi ak bk. That's your first relationship. When it comes to your second relationship, you have to multiply this. Again, minus 2 cannot be 0. You have to multiply this by this, put it on the other side. Multiply this by this, the first term. Multiply this by this on second term. It will become if you look at this two relationship in terms of AK and BK, at every stage you do know every term with index I. And index I is defined internally. See? Index I is defined internally. What you need to do is to define K externally. K could go from 0, 1, up to the case when your stopping criteria is satisfied. At first, you have to put K equal to 0. That will give you A1 minus A0, B1 minus B0. And every summation is given to you because these are in terms of xi, which is given, and A0 and B0, which is given. Again, here you do know this summation because every term is in terms of A0, B0, and xi. And of course, you do have this here. You can solve this linear system for A1 and B1. Of course, this K should also go from 0. In fact, these two relationships is the iterative relationship that I told you. The iterative relationship. You need to incorporate K equal to 0 to find A1, B1. And then you do know A1, B1 incorporated into this same relationship to obtain A to B2. And then at some stage try to satisfy the stopping criteria that you consider. This is called nonlinear parameter estimation. Question?
یعنی همه چیز رو داری A رو B رو فقط بر هر مرحله A کار برنامه یک و B کار برنامه یک رو
یعنی اول شما تو این دو معادله و دو مشهور کار صفر میگیرید A1 و B1 رو به دست میارید A1 و B1 بعد A1 و B1 رو دارید میرید A2 و B2 رو به داشتن A1 و B1 به دست میارید
بعد اون شرطا رو امام میکنید
بله بعد A2 و B2 رو میسید A3 و B3 A3 و B3 رو میسید A4 و B4 تو هر استیجی هم هر کدوم از شرط استاپینگ کرایتریا رو مانع میکنید از سام استیج که این شرط اعمال شد میتونید کار رو متوقف کنید. Question. Remember we talked about this relationship in our previous lecture, and remember we tried to use matrix notation to solve this problem. If you remember, we denote S by this vector. We denote A x1 1 x2 1 x p 1 and then we denote y to be y1 y2 yp. Based on this definition of vector S, matrix A, and vector Y, we realize that A transpose times A times S is given by A transpose times Y. And then S can be written as inverse of this times this question. And this is a very important question. If we denote Sk plus 1 by this, Ak plus 1, Bk plus 1, could it be possible to write down a similar equation like this for this? As an example, could it be possible to write A transpose times A times S? S is given by A and B. You may want to call this AK plus 1. And then on the other side, write down A transpose times something, not necessarily Y, but this difference here. Could it be possible to write down these two systems of linear equation in terms of AK plus 1 and BK plus 1 in this way? And then if it is, what would be the matrix A? By now, this y bar here is this vector. Y1 minus this, Y2 minus this, Y3 minus this, so on. But when it comes to AK, on Monday, I will introduce this matrix, being able to write down this system in terms of matrix, and then if you are working with MATLAB or Python, then because both programs are matrix based, it makes a lot of sense to use this relationship. از حوصله همگی سپاسگزار هستم. تا روز دوشنبه همگی رو به خدا بسپارم.